So, hey, Peter, thank you for coming in today. You got this outstanding prize. It's considered the second highest prize with the ACM prize in computing or for computing. And really the next one will be the Turing Award. So the way your career arc is going, I can see that happening. And you've done so many different contributions in the field of robotics that our audience needs to know what you've done and where it's continuing to go, because they're going to ingest that technology, and you're making so many significant contributions. So very much appreciate you sharing your insights with our audience.
Well, thanks for having me on, Stephen.
So one of the first things that I'm always interested in is, you've got the outstanding arc very early and a continuing substantial global contributions. What were the inflection points that made you this outstanding individual? Could have been when you were 5 or 10, maybe early in school, maybe later in your career. Are there 2 or 3 that come to mind?
Yeah, so when I look back to my childhood and what I was up to then, truth is I was just interested in everything. Anything I could learn about was interesting, whether it's literature, languages, math, physics. I just found everything fascinating. But then at some point I realized that it's hard to be at the top of the game if you try to do everything. And I had to think hard about, what am I actually going to spend my time on so I can really be at the frontier. And so at some point towards the end of my undergraduate, which I did in Belgium, I just got really fascinated, more so than anything else, by artificial intelligence. How is it that humans can think? How is it that humans can make intelligent decisions? And then from there, how is it that it's possible to write a program that plays chess better than the person who wrote the program? And that to me was really fascinating, that it's possible to somehow write these artificial intelligence programs that are smarter than the writer of the program at the thing they are supposed to do. And so that really got me going from a just pure intrinsic interest point of view, but also from a impact point of view. It seemed, even if I cared about everything and I couldn't do everything, maybe by working on artificial intelligence, in some way I could be working on everything, because maybe AI could help everything else. Maybe it could in the future help biology, physics, and so forth. And actually, we're starting to see some of that very recently, that AI is starting to help other disciplines. And so to me, that helped me really consolidate. Let me just focus on AI, because that's most interesting to me. Then, of course, even AI itself is a pretty large discipline. And these days, it's a lot more converged. I mean, almost all the recent advances are in deep learning, and variations on the latest version of deep learning lead to the next breakthrough. But when I started my PhD, which was in the early 2000s, that wasn't the case. AI was still more of a scattered field, and it was important to pick a application domain to tie it to be able to make consistent progress. And so for me, the natural one was robotics. And you might wonder why robotics. I mean, there's other domains, of course, that are really interesting too. But to me, it seemed that if we really care about artificial intelligence and building truly smart systems, the most natural thing is to look at robots, because robots are a lot like us, a lot like animals. And that's where we see intelligence in the real world. The natural intelligence is all in physical embodiments. And so it seemed to me the most natural place to start to try to build AI is tie it into physical systems, tie it into robots, more natural way to make progress.
Well, you definitely are doing that. I mean, and I get it. I get the sort of early interest in physics and everything else tied to science, and then you want to have this global impact, but you want this practicality element. And robotics is really, the most practical, or one of the most practical ways to do this. And even in autonomous vehicles, really the robots, right? There's vision systems, there's some kind of understanding of the environment, and you embody all of that early work. And I noticed early in your career too, I mean, you studied under Andrew Ng, and he's done a lot of work, and he's It's quite a well-known venture capitalist as well. So, and then you went on, you pioneered things like imitation learning and reinforcement learning, but applying it to deep reinforcement learning with deep neural networks. Can you talk about that journey of what excited you, and you know, how did you create these kind of new paradigms that are used so globally now in the robotics field?
Right. So during my PhD days, the way the state of the field was at the time was that the right way to make progress was to combine deep domain expertise with machine learning. And so what we did at the time, we looked at what at the time was one of the hardest open problems in robotic control, which was helicopter flight. How can you have an autonomous helicopter that flies at the same level of capabilities as the most expert, most advanced human pilots? And what we did there is we brought together techniques from optimization-based control, system identification with machine learning, and together it allowed us to have the most advanced autonomous helicopter today still, actually. The helicopter could do flips, things like chaos, tic-tocs, all kinds of advanced maneuvers. This is for RC helicopters that almost no human pilots can actually do. But a big part of it was also learning. It was learning from human demonstrations. We had one of those human pilots showing us what they can do. We collected data, and that was a big part of the process, combined with optimization-based control. But now, of course, the very big thing that happened in 2012 was the ImageNet breakthrough, where Jeff Hinton and his students showed that deep neural nets can be trained from a lot of data to recognize what's in images at a level that was unprecedented at the time, a very big leap forward. And what it showed is that maybe you can start with a purely data-driven approach, a purely learning-driven approach, without all the detailed engineering of specific knowledge into the systems directly. And so to me, that was when you say, hey, where does your reinforcement learning, deep reinforcement learning work come from? I had worked on reinforcement learning quite a bit as part of the helicopter project, but that was not deep reinforcement, it was regular reinforcement learning where many parts are engineered and then some parts are learned. In deep reinforcement learning, the idea is that the large neural network is going to learn everything. So it's not just going to be a little bit of extra at the end to make it better. It's going to be from scratch. It's going to learn everything. And to me, the reason that I thought it was time to revisit reinforcement learning, but now with deep neural networks, was that ImageNet breakthrough from Jeff Hinton and his students in 2012. And so at that time in my life, we thought, okay, this means that things can be learned completely. What is it for image recognition? So what does that mean for learning to control a robot? Can we, for example, have a humanoid robot that we don't program anything into? And maybe it just starts lying on the ground, and it's just lying on the ground, and you just say, I want you, robot, to get up, and I want you to figure it out on your own. And that's really reinforcement learning, where you don't tell it how to do anything. The agent is just being scored on the quality of what it's doing. So the simplest example, of course, is video games. In a video game, there's typically a score. And so you could say, okay, play the game as many times as you want, and then over time, learn to achieve higher and higher score. Robotics is similar, but now we have to come up with the score. So for the humanoid robot, maybe the score is how high up is the head of the robot. The higher up, the better. And so when it starts on the ground, it has to learn to stand up to get its head high up. And over time, it actually learns that. And that to me was really probably the most fascinating result in those early days that we had, that this humanoid robot, this was a simulated robot, was capable of on its own learning to get up. We didn't have to tell it what it meant to get up. We didn't have to tell it, you want to plant one of your hands or you plant your feet. Those were the kind of things that it figured out on its own. And I would say that's generally the beauty of reinforcement learning, is that when you look at learning today, there's really three types of learning. There is supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, it's pattern recognition. You feed in data, and you say, this is the input and this should be the output. And you give a lot of examples. For example, image and a classification of what's in the image, or a sentence in English and a sentence in Chinese. And you give enough examples and a neural network figures out the pattern to go from the input to the output. Even for things it's never seen before, it's going to be able to do it. Now, the trickiness with supervised learning is you need to provide a lot of data that often requires a lot of human effort to provide, because there's a lot of data out there, but you need to annotate it with a desired annotation or output. So for robotics, it would mean that you need to provide the correct motor torques at each of the motors of the robot for every situation to learn something with supervised learning. That's very tedious. Now, with reinforcement learning, what you get is you just score the system. So you might say, high score in the game is good, or standing up, meaning the head is at a good height, is good, or maybe running forward, meaning that the center of gravity of the robot is moving forward and is at a certain height, is good. And now the beauty is that instead of you telling what all the torque should be at all the motors, which is just not really clear how you're going to do that, say what should be the torque commands at all the motors to do running, you just have to come up with a scoring metric. And then the agent on its own will figure out how to achieve a high score. Now, of course, that's also how you train, for example, a dog. When you train a dog, you can't force its muscle contraction and say, this is how you're going to do things. You give it treats or encouraging, you talk to it in an encouraging way, or you might talk to it in a less encouraging way when you don't like what the dog is doing. But the dog is the one who has to figure out how to do it, how to get you to talk nice to it instead of not so nice, right? And that's the beauty of reinforcement learning, because it not only makes it that you don't have to supervise all the details, but also makes it that actually the system could learn to do things possibly better than you can do them, because you're not telling them, the system, do this way. You're telling it, this is what you're trying to optimize for. See how far you can get. And so we've seen that in Go. DeepMind's Go system is better than the best human players. We've actually started to see it in some application domains like chip design, where there's been results where chips can be designed with a computer system that uses reinforcement learning to come up with new designs that are different from the designs humans had for circuit layouts. And so there are interesting opportunities here in reinforcement learning to go beyond even what humans can do. And now, of course, to go back to what I said earlier, there's 3 types of learning. The third type of learning is unsupervised learning, where there is no input-output annotation. There's not even a score function that you provide of what's supposed to be maximized. You just have data. And you might wonder, how can we learn from just data? That seems, if there's no score, there's nothing we're supposed to match. And the idea there is the following, and we spend a lot of time on this these days in my lab, and the combination of unsupervised learning and reinforcement learning. The idea is that when we watch the world, what's happening in the world, we're learning from that. We're not trying to optimize anything, we're just watching. From that, we understand how the world works. And then when we're asked to do something, we can do it much better than if we had not had a chance to watch things happen in the world. And that's what unsupervised learning is about. Can robots watch videos, let's say on YouTube, and from that learn how things can be done? And then when we ask them to do something, be much quicker at acquiring a new skill.
Well, you definitely have made all of these, remarkable contributions. So you're talking about sort of the formally your work and things like trust region policy optimization, your work in generalized advantage estimation, sort of the technical areas of you're really quite famous for. I mean, so widely cited and used. Can you talk about your work, when you're looking at things like domain randomization, sort of give sort of the English sort of what that word is, and also hindsight experience replay and things like that?
Absolutely. So when you think about reinforcement learning, it's trial and error learning. The agent is going to learn from repeated trial and error. Now, if you want to apply this in robotics, your robot is going to go through repeated trial and error before it's going to do the thing you want it to do. And in many ways, that's beautiful because it's learning. You can watch it learn over time. But in other ways, at times, it can be impractical. Because if your robot really doesn't know yet how to do things, it might damage itself. It might do damage to the environment it's in before it actually acquires the skill you want it to have. And so doing real world, directly in the real world reinforcement learning can be very, very costly if you're going to run it that way. It might take a long time because it might require a lot of trial and error, and you might be really busy repairing the robot and fixing up the room or environment it's in. So it's very natural to then say, why not work in simulation, right? In simulation, the robot can't really break things. It's a simulated robot. You can always reset the simulator or reset the computer as needed, right? Also in simulation, you can often run things faster than real time. So you can learn faster than you could do in real time. And you can run many versions of your program in parallel. So you can be collecting data faster. Just depends how many computers you're willing to spin up. And so a lot of advantages there in learning in simulation. And so a lot of work is done that way, but there's a catch, of course. Simulators are never perfectly matched with reality. And so if your robot is going to learn purely in simulation, and if your simulation is not perfectly matched with reality, then once it's done learning and you load the neural network onto the real robot, it might actually fail. In fact, most likely it won't succeed. And so the question is then, well, can we match up the simulator more closely with reality? Because if we can do that, then there's a higher chance of success. And that's an approach that I have followed many times, and many others have followed many times, and it is quite a reasonable approach and a good approach, I would say. But it's typically very hard to get a perfect match between simulation and reality. And so in the domain randomization work that you referred to, Stephen, we thought about this, and the idea we put forward in that paper was essentially showing that maybe your simulator does not need to be all that perfectly matched with reality. Instead, what we're going to do is we're going to build many versions of the simulator, and they're all going to be different. Maybe the friction properties between two surfaces are a little different between the feet of the robot and the ground in the different simulations. Maybe the mass properties of the robot are a little different. Maybe some delay between torque command sent and torque command activated at a motor is a little different in different simulators. Maybe the camera is set up in a slightly different position on the robot's head, and so forth and so forth. So there's all these variations that we don't know how to perfectly match with reality. And so instead of trying to somehow find a way to perfectly match it up, we say the things we don't know, we're going to vary them. And so we're going to have maybe 1,000 or even 10,000, 100,000 million different versions of the simulator that are all a bit different on these parameters. And so now you might say, well, that's kind of crazy. Instead of trying to get the closest to reality, you're actually making it different in every simulator. Now, what's good about that, it turns out, is that if a single neural network can learn to control the robot across all those simulators, even though not a single one is matched with reality, the fact that there's this single neural network that's learned to control the simulated robot, no matter what version of the simulator, makes it actually very likely it'll also succeed in the real world, because you've learned something very, very robust that can handle a wide range of variation. And then hopefully that means it can also handle the variation it encounters in the real world. And so that's domain randomization. We randomize the domain the robot is learning in. And the domain, well, that's the environment of the robot, that's the simulator.
I guess that's really fascinating because there's always this barrier challenge with machine learning and AI, and that aspect is very narrow. And what you're doing is you're giving it this sort of this generalization capability, which is this big challenge, right? If the more we can generalize, then we can maybe reach some kind of form of artificial general intelligence. Do you think we're going to get to this sort of massive change where we do have sort of true artificial general intelligence, or and some major breakthrough, or is there something that you're working on that can lead in this way, perhaps in your work with Hindsight Experience Replay, but a manifestation, an iteration of that work where you can use smart, reward, and goal-oriented environments, which is tied to your domain randomization as well. Do you see it moving in that direction? Are you going to be part of that change, and how?
Yeah, so I think that's pretty much the most frequently asked question, and also one of the hardest ones to answer, of course, to have a precise answer, because artificial general intelligence is this idea that we would end up with something that's as smart or even smarter than humans, and in a general sense. And to make this a bit more concrete, we already have computers that are smarter than humans at very specific tasks, right? There are video games computers can play better. There are regular games, classical games, chess, Go, checkers, computers can play better, and so forth. But the best computer Go player actually doesn't know how to physically move a Go piece on the board. All he knows is to think through the different moves in the game and then display a command on a computer screen. And so the thing is, the big missing piece, if we look at AI today, is that artificial general intelligence, the ability to have a system that is extremely general in its capabilities, that can learn new things quickly, the way humans can learn new things quickly in new environments it's never been in before. Maybe it's never been in your kitchen before, yet it somehow knows how to do things in your kitchen. Maybe it's never driven, in a certain city before, but it just knows how to drive there without a map, nothing like that needed. It just knows how to generalize, right? And so generalize across all these different tasks. And so personally, I think it's hard to predict, of course, when we'll actually get to human intelligence. But personally, I think it's really fascinating to think about this notion. Can we have our agents, our AI systems, learn things, internalize things that are maximally generalizable, that allow them to learn other things, solve other problems more quickly in the future, rather than being focused on a very specific problem during learning, focus on somehow building a foundation of knowledge that allows to learn faster in the future. And so I've actually been thinking about this quite a bit. And the Hindsight Experience Replay work you bring up, Stephen, is of course related to that. So let me quickly highlight that, and then I'll look at the more general picture. So Hindsight Experience Replay, the idea is the following. And this is a very effective, I would say, modification of the standard reinforcement learning paradigm, which just directly optimizes rewards. Hindsight Experience Replay is a very effective modification that allows the agent to learn from data more effectively. Imagine your agent is trying to do something, and you give it, let's say, a reward for achieving success, right? But it hasn't learned how to achieve success yet. And so now it's trying, and it always gets 0 reward because it just doesn't know how to do it yet, right? But if it always gets 0 reward, then it can't learn anything either, because everything is equally bad. It's always 0. So then it really has to do random trial and error to hope to just coincidentally come across the thing that does get you reward. But if the thing the robot is expected to do is complicated, well, then to randomly run across a success with random actuation of the motors of the robot, it's very unlikely, right? So in Hindsight Experience Replay, the idea is the following. No matter what the robot does, we're going to let it learn from it. We're going to say, okay, I didn't ask you to, let's say, fall down instead of running forward, because I asked you to run forward, but you fell down. But if I had asked you to fall down, you did the right thing. Or if I had asked you to, first fall on your right knee and then fully falling down on the ground, you did the right thing for that request. And so what you get here is a notion that this agent, this robot, is learning a lot about what kind of commands it already knows how to satisfy, what it has done in the past. It can internalize all these concepts such that it over time they can generalize. It says, I've learned to fall down, I've learned to fall backwards, I've learned to fall sideways, I've learned to get my right leg in front of my left leg. And so it learns all these things. And by having a wide range of existing skills that are maybe easier to acquire and easier to randomly run across, it can build up a skill repertoire that makes it easier to later then learn the thing you actually care about. And so that's hindsight experience replay. But when we think about AGI, a much more general intelligence, I think what we were thinking about is in some sense a generalization of this. If we want to get there, and this is not necessarily the guaranteed path to get there. I mean, people don't know how we're going to get there. We're not there yet. But if I think about how do we get the most general AI system, I think about a system that has to learn as much as possible from the data that's available, right? And so hindsight experience replay is a way to learn as much as possible from the data the robot is collecting on its own. That's nice. But there's so much other data out there too. There is so much data on the internet that's already collected. The robot doesn't have to go collect that data on its own. So when I picture kind of the future of robot intelligence, what I picture is a robot that has watched a ton of YouTube videos, other videos that are online. And it doesn't just watch them, it also looks at the annotations that are with them. It might say, oh, that was a video of somebody chopping carrots. That was a video of somebody, I don't know, maybe playing tennis or basketball or something. And so it's learning from that, the connection between what's in those videos and how we in language describe what's going on. But then it's also going to be learning to predict the future, because as it's watching a video, a natural prediction problem to train the system on is to say, what if I don't tell you what comes next in the video? Can you fill in the blank? Now, of course, it's not possible to deterministically know exactly what's going to happen because, I can move my right arm up, my left arm up. You cannot predict what I'm going to do next from just watching the previous part of the video. But you can predict a probability distribution over possible futures, right? And so can we request our deep neural networks to learn to predict probability distributions over possible futures? Those are the kind of tasks we can give them. And we can do the same thing for text. And in fact, in text, in the language domain, that's something where we've seen a lot of excitement in the last 5 years out of OpenAI's GPT models, Google's BERT models, and so forth. We've seen text models that can predict what comes next in an article. Not deterministically, but it can predict possible completions that are plausible. And likely that'll include the one that was there if you give it a set of predictions that it's allowed to do. So we're going to want the same for videos. Videos are a lot bigger in terms of amount of storage, amount of data you need to process. But ultimately, I think that's going to be at the core of how we get to more generalized robotic capabilities. These deep neural nets will be largely trained on videos. On these videos, they'll be trained to predict what comes next, predict maybe what was in the past, predict to fill in the blank, and so forth. They'll predict associated text with those videos. And there's, for practical purposes, there's essentially infinite video data on the internet for our robots to learn from. And I think 99+% of the data our robots will be trained on will be that. But then that doesn't mean the robot know how to do something themselves. They've just been watching videos effectively. So how do they know about their own hands, their own legs, their own camera system, where they collect data from, how they move their head? So that part, in my mind, is going to be reinforcement learning. The robot's going to combine the same deep neural network is going to be both doing learning from videos and text on the internet and reinforcement learning in a single neural network, just the way humans have a single head, a single brain that they use to learn from what they see in the world, but also learn from their own experience. So that's going to be brought together. Now, when I think about reinforcement learning in that context, I don't think we want to give the robot feedback at all times we want to give it sparingly some feedback, but we mostly want it to be capable of learning on its own. And so the type of reinforcement learning that's going to happen is not going to be win this game, win that game, or achieve this task or that task. It's mostly going to be unsupervised reinforcement learning. It's reinforcement learning where the robot, or in general the agent, gets rewarded not for completing something specific, but for being curious about the world, being curious about what will happen if I do this, what will happen if I do that. And so this robot will try a wide range of things on its own to better understand how it can interact with the world. And if you transpose this onto humans, think of it as play, right? When you have children, they just play. They explore the world by playing. And it's thanks to exploring the world by playing that later they can learn other things more quickly that you might care about. Maybe you want them to clean up their room, but it's not that from day one you train them to clean up their room. It doesn't make sense. It wouldn't be fun, but also it wouldn't be an effective way to learn because it'd be too focused. By allowing for play, you allow much more generalized learning. And then later you can have children or robots learn more specialized things more quickly. And so when I envision the future kind of very large neural networks that will be the brains of our robots, 99+% learning from data on the internet, mostly video, and then unsupervised reinforcement learning, think of it as play, to learn about its own body, interaction with the world, and then a little bit of learning with human feedback to learn about the specific thing you want the robot to do for you.
Just it's kind of fascinating. I've been around a long time, and I remember expert systems were gaining so much traction back in the early '80s. And you had Doug Lynette, and he created this, created the system, and it still exists. He's got an iteration of it, still exists. And then you have AI going through this winter, right, where there isn't sort of a lot of progress. And then, as you mentioned, Hinton at the ImageNet, it surprised everybody. And you had Jeff Dean then and Andrew create Google Brain based on that work as well, right? And they got this thing about cats. It became quite famous from having it looked at the internet. But then you have these sort of outlier, but really great research. I'm thinking Pedro Domingos, and he wrote this book, The Master Algorithm. And he talked about sort of 5 main schools, and he was suggesting that if you could combine them in some way, so not just deep learning, but all the other sort of schools that are in machine learning, if you combine them in some way, you can get more generalization. And then you have even like Julia Pearl, where he's created this mathematical causal model, and he can actually represent what's happening within that causal model. And he said, if you do that correctly, then you can get more generalization. And he even put an article out in the ACM, the Association of Computing Machinery, on sort of 7 factors that you should consider. And he's even been funding some of this work, right? Because very few people were initially writing papers based on his work. What do you think about all of this? Do you think that there's enough capability in all of the iterations that are occurring in deep learning that it can just get there? Or do you think it's going to have to be some kind of hybrid amalgamation that ultimately results in what you're talking about? But you also mentioned like all this progress that's being made on the language model, the transformer models, like I call it GPTX now, because GPT-3 is 175 billion parameters, but the Chinese came out with one that's 1.7 trillion, something like that. Google probably has one. There's probably GPTX, which is over 100, or let's say in the tens of trillions. And then even NVIDIA, if you look at Jensen Huang and some of his keynotes, or some of the work that Keith Streer talks about, the head of AI, they're suggesting that even next year, there's going to be models, at least on the language side, that are going to be over 100 trillion. And what does that mean? And can that then factor in, like you said, in the video, or get to this generalization? There's a lot of thinking there. If you can corral all those cats into some kind of cohesive narrative of where that you think all of that's going to go.
Yeah, I mean, just zooming out for a moment, I mean, the way research is done, research is about trying new things, coming up with new ideas that might be the next big breakthrough, right? And so it's very natural, I think, for researchers to think about, okay, maybe this deep learning thing is not everything. Maybe we're going to need other things. And, depending on the researcher, they might either, quietly try to make progress on it, or they might want to, declare like deep learning is not everything. We need other things. I think if you look at the past 10 years, for 10 years, 2012 was the image at moment, right? There's been a lot of people, small fraction relative to the entire community, but a good number of people who like to speak up on, we'll also need other things. And I think that's not a bad thing. But the truth is that in the last 10 years, every single breakthrough that has been of high impact in AI has been deep learning. Like there's literally been no exception that I'm aware of, right? Every headline, every major thing. Is it possible that something happened behind the scenes that is the seed for something new that in the future will be really important? That's definitely possible. I mean, Jeff Hinton was working on deep learning since the 60s, 70s, and it didn't really make its breakthrough till 2012. So obviously something similar, it's possible, it's happening. But I would say if we look at the frontier just moving forward in the last 10 years, there's only been one thing. It's been deep learning all the way. That makes, of course, a lot of people even more excited and hopeful that maybe there's something else that'll come later. But it's been always interesting to see these conversations, right? When people say, I think we need something else, I think the natural counter question has to be, what is something we cannot do today? Like, what is something we really don't know how to do today? Something you can point to, we cannot do X. And then let's see what gets there. That's a very productive way to think about it, right? That's where you turn it from being a skeptic or being, maybe it's a skeptic or maybe a hopeful to come up with the next big thing that's even bigger, into a concrete, constructive way to help us all make progress. And maybe 10 years ago, people would have said, or even 5 years ago, they might have said, art. Art is something intrinsically human. There's no way deep nets that we train are going to be able to do art. But if we look at today's art creations from deep neural networks, you can just prompt them and say, bunny on the moon planting a US flag or something, and it'll actually have an artistic rendering of that, right? And so it's really interesting that anytime people have mentioned specific things, fairly consistently, they get knocked, they get checked off with larger, more advanced deep learning. It's not that deep learning hasn't changed, right? The deep learning of 2012 is not exactly the same as the deep learning of today. Architectures have changed, best practices have changed, not to mention the amount of data, the amount of compute used has drastically changed. So right now, personally, I see challenges. I see things we can't do yet with deep learning. But personally, when I look at my research agenda, I think the most likely path, at least that I see now, to address some of the open challenges, such as a much more generalized intelligent system, is by building on what we have in deep learning and making it more capable, rather than coming from a completely different angle than what we have today. It seems there's so much room for more. When we think about, today we don't have good video prediction models. It's pretty clear to me that if we had, let's say, 1 million times the compute we have today, that we should end up with good video prediction models. Once we can pre-train our neural nets with video prediction, well, what does that open up in terms of opportunities relative to what we've seen in language in recent years? I think it's going to be tremendous for things like robotics, but any kind of visual intelligence. And so to me, that's the more natural path forward. I applaud the people who try a different path. I think it's great. I think it's important that not everybody follows the same path. But to me, there's this path that seems so obvious that there's so much headroom for the next thing that I'm pretty excited to work on that path and see how far we can get.
When I analyze your career, I see this real sort of interdisciplinary approach. So do you also look at, there was this researcher back about 15 years ago that, Yamanaka, and he came up with this Yamanaka 4 factors where you can take adult cells and regress them into stem cells. And then, excuse me, people are taking that work. And it's fascinating work because they've taken that work and now they're growing organoids, right? And these organoids are things like brain organoids or sort of like mini brains. And you can even see electrical patterns that mimic what you see in fetuses up to maybe about 10 months. And then it seems to stop. And why does it stop? They're thinking it's because it's not getting the sensory information that a normal brain would go under. And then there's sort of these ethical questions. How far do we allow this to grow? Are you looking at some of that work to see what's happening? Because you can get very granular now in that activity that's occurring and trying to mimic that in some fashion with deep learning algorithms or, the work that's in the neuromorphic side. I mean, last week I interviewed Jack Gondero, who won the Turing Award. But he talked about neuromorphic. They're looking at it at Oak Ridge. They're looking at photonic technology together with their supercomputers and quantum computing and so on. And they're looking at applications and simulations that you mentioned, but very, very detailed simulations, or what Jensen Huang is doing with his version of the metaverse as Omniverse, where you can simulate robotic action and then take it into a factory. Are you looking at some of that other work? So to the biological aspects, the attempt to put that biological stuff into silicon, and then maybe some of these other paradigms that are out there, like quantum computing and also supercomputing, which is all exascale now, right? There's 3 in the US that are exascale, so which is a billion operations per second, right? So
Yeah, so when I think about research, it's always a combination of looking at the tools you're already working with and somehow trying to find inspiration to push them further. And pushing them further often means getting inspiration from related fields or observations of things humans can do maybe at a certain age that our AI systems cannot do at all. And like, wow, how can a 2-year-old do this and our AI systems don't even get close to this? So for example, at Berkeley, I have some collaborations with psychologist Alison Kopnick, where we look at how do children explore how to play in video games versus how do our current reinforcement learning agents explore in video games? What are the differences? Why are there these differences? And that's at a higher level than their neuron activations. It's at the behavioral level. What do we see occur in their behaviors? I think it's super interesting to see if we can get anything from the direct neuroscience and direct measurements of neuron activations and so forth. Traditionally, that's been hard. And what you're alluding to, these opportunities might start to open up, but traditionally that's been very hard. And so traditionally, a lot of the inspiration for me, and as I see many others who have had breakthroughs in AI, has come at a slightly higher level of abstraction. It seems that in the cognitive development of a human or animal, this is the sequence of things that get acquired. Or evolutionarily, early on, these were the things that were possible, and later these things became possible. So that might inspire the order in which we try to investigate things and get to certain levels. And then, another way to think of it, the other things you're alluding to is indeed, the more compute cycles we have, the more progress we can make more quickly, because our experiments will be faster and larger and so forth. And so there's kind of 2 axes. One is to get more compute. The other one is to get more compute with less power, so we can put it in our devices more easily. And I think there's a lot of breakthroughs we can expect in the next several years from existing companies like NVIDIA and so forth, but also many startups that are working in the computer chip space and try to innovate and try to come up with new paradigms that are, I would say, more tailored to neural network compute. Because traditional computers, they're built for all kinds of purposes. They're not built specifically with neural networks in mind. And so when your chip is not designed directly with neural networks in mind, well, it's not going to be as optimized in how much compute it can produce when you want to run neural networks through it. And so I think that's a pretty big trend we're seeing that's quite important for the field. And so one obvious thing is just the type of compute that happens. Essentially, it's just matrix multiplies more or less. So chips specialized to that. And of course, Lin Pack and so forth, is specialized on matrix multiplies. So strong connection there with this year's Turing Award winner. But then there's also things like, do you need exact computation? With neural networks, it seems that maybe 8-bit calculations can at times be good enough. You don't need 32 or 64-bit. Now, all of a sudden, you open up a lot more compute cycles because you get away with less bits. Can you go to analog? I don't know. I'm not an expert in that, but those are the kind of things that are interesting questions to ask, right? Can analog be a more efficient way to get these approximate calculations done and so forth? Now, I should also highlight there's a whole other side of the spectrum. It's like, okay, where do we go? But there's also, where are we today, right? And I think if we look at where we are today, we can already build many applications. And we talked about it earlier a little bit, but there's so much more we can do, but there's also things we can already do today. And that's why, if you think about robotics, so far we talked about it as what's the future? But I can also think about what's today. I can today, we actually have a company, as you know, Covariant, where we do this exactly. We can put a robot in a warehouse to go help out, right? And that is using today's deep learning technology, a combination of supervised learning, unsupervised learning, reinforcement learning to do reliable pick and pack operations in a warehouse. And the reason I'm bringing it up is that, one, it has very big impact already today, but two, Stephen, your earlier question, all these other ways of encoding knowledge, right? Where people just hard code knowledge. When we started Covariant, we told people we're going to do 100% learning based. We're going to learn. And they would say, well, but aren't there things you can hard code? Can't you just say if then else? This if then else is correct, right? And like, it's usually correct. But when it's wrong, how are you going to overrule it? Once you start putting in rules, then you have to put another if then else, another if then else. And at some point, things become unwieldy. The classical AI example is, of course, birds can fly. But then what if it's a penguin? Or what if the bird injured their wings? Then this bird can maybe not fly. So then birds can fly except when their penguins are injured their wings. And so things get very unwieldy very, very quickly, right? Is it still a bird because it cannot fly? Now, these if then else rules have that issue when you logically try to constrain things. And so what we said at Covariant, and which is part of our core philosophy, if we learn everything, you can always correct things by providing more data. If it doesn't understand something right now, you provide more data evidencing the thing you want it to understand. You train it on that additional data, and it'll absorb it, assuming your neural network is correctly architected, large enough to absorb the data and so forth. And that's now the beauty, because if you start hard coding things, as you're alluding to, there are some classical AI approaches that hard code all kinds of facts about the world and so forth. You can actually use that as a data engine. You can say, this is part of my data. Anything you want to hard code about the world, we're not going to hard code it. We're going to use it as a data engine. It's going to be part of our data. And so it'll generate data. That's interesting, that our system can learn from. But it's not going to take it as rules. It's going to take it as data examples of things that can happen in the world. And I'll see examples of that. Those examples, things that come from the actual world, combine it, and from that internalize the most accurate model that I can put together for what it's faced with. In our case, it's robots doing pick and pack, but this philosophy is actually much more general, to avoid this notion of hard coding, but not throw out things you can hard code completely. You can still use them as data engines.
So Pieter, I'm just doing a time check. You have a hard stop, right, at 9 Pacific or not?
I can probably run 5-10 minutes over.
Okay, that's great. Because we haven't unpacked yet. You're director of this robotics learning lab, which is really famous. Co-directed the Berkeley AI Research Lab, which is also world famous. I wanted to get more into covariance, so good. I'm glad you talked about that. Your past exit, which is Gradescope, but you also have a venture capital group called AIX Ventures, and then your robotics brain podcast. So let's say in the next 10 minutes, if we can get some coverage of what you're doing now and where it's going. So, you know, it's really, really exciting what you're doing at Berkeley. And can you sort of map out where you see that going into the future? And some exciting things that you're working on that people can relate to, then you think will have some practical applications.
Yeah, so just to make sure I understand the question, are you trying to map the Berkeley research to future research, or mapping how it connects with all the things happening at AIX Ventures and at the Robot Brains podcast and Covariant?
No, those will be separate. So I'm going to treat them as separate. So on the research side, where do you see that going? What's really exciting for you? You've covered some of this already, but maybe there's areas that you haven't mapped out yet. And do you see, can you predict some of the practical application just from the pure research side? Because your labs are so famous, right? So,
So personally, I'm super excited about robots that combine learning from all the data on the internet with their own experiences, where most of the data will come from the internet, video, possibly also text, and a little bit of experience comes from themselves. Not a little bit because we're constraining it. The robot should collect as much data themselves as they possibly can. But even if a robot is collecting as much data as it possibly can, it's going to be so much less data than is available on the internet that's collected by billions of people and posted on the internet, right? So it's always going to be a small fraction only that the robot can collect on its own relative to what's on the internet. And so the ability to somehow learn from both, a single system that learns from both and has the ability to quickly acquire new skills, that's really what's always on my mind. If I think about the research at Berkeley, it's how do we somehow pre-train a robot such that it's ready to learn new things really, really quickly. Ideally, pretty much on its own when it's learning the new things, but mostly pre-training from data that's available online, because that's the biggest data source we have today.
You know, I guess this gets into this sort of like one shot, quick shot kind of concept, right? And small models as well. I mean, I see so many ramifications of this, and you're leading this work, and you also have a community aspect. You share videos. You're very much into the open source, so you're really developing and have developed an amazing community out there, and you're recognized for that in your ACM award as well. Okay, let's go to now your venture work and the fact that you co-founded Covariant and you explain what you're doing. What's your ultimate goal for Covariant? And then we'll talk a little bit about Gradescope, which has already been acquired. And then I'll get into your ventures, but those, you know, sort of separate buckets. So let's talk about these companies you've started. Are you and have exited? Are you thinking of creating more companies and things like that? You know, what's your mind frame in that area?
Yeah, so it's always hard to predict the future, but I can share the past, how the existing companies came about, right? So Gradescope is a company that provides AI to help with grading of homework, exams, projects. And this was just, I mean, it's such a pain point to grade homeworks, exams, projects of students, for instructors, for teachers, for teaching assistants, and so forth. And so this came about from just my teaching work at Berkeley, where it just, I mean, grading on paper, these paper stacks being passed around, it just seemed, you know, from a different era. It's not what we should be doing today. And so the thinking was, if we just scan that work, or students just scan and upload, because most of them anyway had to print it out, their homework, to hand it in on paper. So either way, let's keep everything digital or turn it digital and see what we can do. And so that's what I built with a few of my students at the time. And it's been acquired, as you alluded to, by a bigger education company at this point, Turnitin. It still lives under its own brand, is used in many, many, many places to save people time. And so this was just like a just obvious pain point that just needed to be addressed, both for my own life, but also for all my colleagues and so forth. Covariant is a bit different. So covariant is something that I see more as a very long time coming. It wasn't like, oh my God, and now run into this pain point, let's address it. It's just the notion that in the future, robots should be helping us with pretty much everything, right? There should be a robot organizing my laundry. There should be a robot cleaning my house. There should be a robot cooking a meal for me, maybe. Should be a robot helping us build the things that we build in factories. Should be robots sorting through objects in warehouses and fulfilling orders. Should be robots doing so many things, right? Freeing up our time to do other things. And the reality is it's not there. If you look at it, I mean, if you look around in your house right now, you probably don't see a whole lot of robots. Maybe if you're lucky, there's a Roomba roaming the floor, but that's probably it. And so why is that? And what are robots doing today? Well, if you look at the majority of robots, what they're doing is they are in car factories and electronics factories. And the reason they are there is because they're mass production places where the same thing gets built over and over and over. And it's literally the same thing in that these robots can go through the exact same motion, pre-programmed motions, every single time. And that's enough to build a car. And so it's a beautiful orchestration of pre-programmed motions. That is what's happening. And that's why, even though it's beautiful, when you watch it, it's amazing. They can do precision welding, assembly, and so forth. It's just that. It's pre-programmed motions. If we have more capable AI, naturally, we should be able to go well beyond pre-programmed motions. The robots of the future should be robots that look around, react to what they see, understand how to act in that world. They understand what they're faced with, how to react with, and exactly what way to achieve their goals. These robots of the future, what's missing is not the mechanics. What's missing is the brain. And so that's what we're building at Covariant. We're building the brain for the robots of the future. Now, in what I just described, you might naturally dream of robots that, come in your home and take care of a lot of things. And that is part of the future. But at Covariant, we're focused also near term. Like we're building a very general brain for robots, but we also want to build a business today. And from that, expand the business to other use cases, of course. And we found that the most natural place for more intelligent robots to kind of come into the world is warehouses. Warehouses, to many people, might sound like factories. Factories, warehouses, often used in the same sentence, right? But warehouses are very different because in warehouses, let's say you go to Amazon warehouse, Walmart warehouse, Target, and so forth. There is hundreds of thousands of different SKUs, stock keeping units. This is a type of items that are stored. And this changes all the time. Their packaging changes all the time. Exactly where they are located, even within a bin, how the clutter is presented to the robot, it's always different. And so what it means is that a robot that just blindly executes pre-programmed motions is useless to manipulate objects in a warehouse. We need much smarter robots. And so that's what we're building at Covariant, robots that actually, through learning, have acquired the ability to do very reliable pick and pack in warehouses. When I say pick and pack, it turns out there are many, many incarnations of that. It's a general skill that has many specific applications. It can be put to light, it can be sorting onto a conveyor, it can be singulation into maybe a pocket sorter, it can be fulfilling an order directly out of storage bins and so forth. It can be the other way around when things arrive in the warehouse to sort through them and decide where they have to be stored in the warehouse. So a lot of different tasks, but at the core, it's pick and place or pick and pack. And it's a massive growth area. And what we see is that there's just a lot of demand to get automation into these warehouses. And so that's where initially we're bringing the Covariant brain, the Covariant robots, because we bring full solutions to these places, not just a brain in a box, and then you have to figure out what to do with it. Actually, the customer will get a full solution that, sometimes we deliver it fully ourselves, sometimes with partners, but either way, ultimately the customer has a full solution available to them that does whatever they need done at that location in their warehouse.
Yeah, I mean, the opportunities could make your company a 100 billion plus company, right? I mean, it's like if you look at what's happening with GPUs and NVIDIA, I mean, they're 3 times larger than Intel. I mean, it's just incredible, right? So, and okay, let's get to your founding investment partner with AIX Ventures, which is a venture capital group, and what I guess it's a robotics and AI that you're focused on. So what's your investment thesis? Very early on or later on in terms of investments? Are you working with government and so on with your venture capital group? What's sort of the basis of this AIX Ventures?
Yeah, so the foundational hypothesis here is that AI is going to enable building so many new products and so many new companies that this is a really good place to be investing into. I mean, AI can impact robotics, as I talked about with Covariant, but it can impact many other types of robotics, right? It can impact drone technologies, it can impact healthcare, it can impact work interfaces that we use to be more productive at the work we do. It can impact legal, it can really impact anything we do as humans, because AI is kind of what makes us special as humans is intelligence, and AI is the artificial version of intelligence. So it can impact pretty much everything we do, so many new product possibilities. So to me, it's very natural to expect that there'll be many, really impactful, exciting companies emerging in the space where AI is enabling to do something new. And X here refers to, it could be anything. It's AI enabling something else to be built. It doesn't have to be, we're just building AI for AI's sake. In fact, probably very few companies will build AI for AI's sake. It's not clear that that's a natural business model, but AI for X, where X could be pretty much anything. Now, of course, you might wonder, well, why am I spending time on this, right? Venture capital is a bit of a different world, though closely related, of course, to technology, but it's the investment side of it. What happened for me personally is that over the years, through my activities as founder of Gradescope and Covariant, and through the fact that there are more and more companies being founded in the AI space, and my expertise, my core technical expertise in AI, I ended up naturally becoming advisor or early stage angel investor into AI companies, right? And so about a half year-ish ago, I was exchanging notes with my good friend, Richard Soker, who also founded a couple of companies and was chief scientist at Salesforce for many years. And we're just exchanging notes on our angel investing, and we're like, hey, maybe we should think of a way that we can do this together in a more structured way and allow other people to co-invest with us. And then the natural way to do it is to set up a venture fund, because people can put money in the venture fund, which allows them, we put our own money into it also, of course, and then they're effectively naturally co-investing with us as we make investments. From there, of course, we realized we don't want to just be the two of us. Two of us are so busy. He has his company, U.com. I have Covariant in Berkeley. We don't have a ton of time to spend on this. We want to spend a small amount of time that's very high leverage, where we can make a difference. But then we need to find other people who are full-time, who can do all the other work that also is really critical in a venture firm to happen. And so there is several other people at AIX Ventures who were full-time, who were just purely focused on AIX Ventures as their main job, whereas Richard and I, as well as Anthony Goldblum from Kaggle and Chris Manning from Stanford, the four of us are essentially focused on the high leverage things, where you might spend 5 minutes here, 10 minutes there, be able to help a company with the right intro or the right insight. And so for me, it's a very rewarding thing to be doing, because it's something I spend extremely little time on, but with the very little time I spend, I have extremely high impact. And that's fun when you spend a very small amount of time, yet it has a ton of leverage, and you can be really helpful to people starting a new company in a very interesting space, and just a little bit of work here and there, a tiny bit of effort, as much as can be helpful, but just ultimately ends up being small effort for very high impact, which is always a lot of fun.
Well, I'm in investment, so I can relate. And I just want to type some loose ends just for the audience. You talked about analog computing. You recommend they look at Hava Singleman's work and using the stochastic aspect of analog and getting some meaningful computational capability out of that. Philip Wong, a Taiwan semiconductor, he's looking at high bandwidth in-chip memory, but would work well with AI and so on. I'm just going to recommend to the audience, they've got to listen to your Robots Brains podcast. I mean, all of the just a marvelous guests you have on there, and great topics. The last question is, any sort of recommendation you want to leave to the audience?
Yeah, so I mean, that's a very general, open-ended question. Let's see. Well, maybe I'll have a recommendation a bit more specific to the AI space, and maybe to younger generation, because it's hard to give super general advice to everybody. I think AI is super exciting, and I think one of the amazing things is that it doesn't require a crazy amount of studying to get up to speed. So once you're familiar with basic undergrad math, some linear algebra, some vector calculus, and undergrad level, couple programming courses. Python is the go-to language in AI these days. So familiar with Python programming and very basic math, you can start diving in. And I think that's part of the beauty and part of why we're also seeing an explosion of applications being built. If you want to be at the frontier of research, you have to put a bit more time into it, of course, to really understand where things are headed and where you can contribute. But even then, it's not the kind of thing where it takes, an inordinate amount of time to be able to start doing something interesting. So often when undergraduates come to me at Berkeley to get involved in research, I'll point them to a total of 4 courses, maybe a course that's kind of a basic intro to deep learning course, a slightly more advanced deep learning course, then a reinforced learning course, an unsupervised learning course. And through the combination of those 4 courses, they are really starting to be up to speed on understanding a lot of things happening today and be able to build things themselves. And so I think that's really fascinating. That's such a powerful technology is really learnable in a relatively short amount of time. And so, yeah, it's exciting days.
Well, thank you again, Peter, for coming in today. And again, congratulations on achieving the ACM prize in computing. It really is a remarkable inflection point in your career. And I can see a Turing Award coming at some point later on as well. So again, thank you for taking the time.
Stephen, thanks for having me. This is really fun.